Hello, my name is Omar Al-Basri. I'm one of your head PIs for Digital Logic this semester, and I wanted to go through some motivation for the components that you'll be using in Lab 2. So, let's say that after your home security system in Lab 1 got lots of customers, you're faced with the prospect of having to monitor two properties. You want to be able to check if either property has the doors locked, but disaster strikes. You only have one LED. If you have only one LED, how can you monitor both houses? Something like an OR gate may come to mind, but this only tells us that at least one property has the doors locked. Similarly, an AND gate only tells us that both properties have their doors locked. What we need is a way to switch what system we're monitoring. The idea is this: a switch that we can flip between monitoring property 1 and property 2. If we model the switch as a binary input, we're looking for a truth table that does the following. When the switch is 0, we want to monitor property 1. The output should be the lock status of property 1. When the switch is 1, we want to monitor property 2, so the output should be the lock status of property 2. If we design a truth table according to the following, where S is the switch, P1 is the lock status of property 1, P2 is the lock status of property 2, and Y is what the LED should display, we end up with something that looks like this. You can see that when S is equal to 0, Y is just equal to P1. But when S is equal to 1, Y is just equal to P2. The important thing to notice here is that when S is equal to 0, the value of P2 has no impact on Y. And when S equals 1, the value of P1 has no impact on Y. Knowing this, we can make the truth table a bit more compact. The X's in the truth table represent don't cares, which means that regardless of the value, the output stays the same. This essentially condenses two rows of truth tables into one. Rather than writing out P2, 0, and 1 when the output doesn't change, we can put an X here to represent that we don't care what the value of P2 is, the output is going to stay the same. Equipped with our truth table, we can now make a Boolean equation for our component. This Boolean equation represents a two-input multiplexer, which takes two inputs and allows you to switch between them. You can see this represented by the not S and S. Switching to a more classic example of what the component looks like. While this example is a bit contrived, multiplexers are some of the most common components seen in digital circuits, and they have a lot of real-world applications, as you'll see in Lab 2. While a two-input multiplexer is great, the real world often has more inputs. So what do we do in that case? We have two main options. Number one is to develop a longer Boolean equation with the same principles. Instead of just S, we now have S1 and S0, which together form kind of a binary number representing which input we want to go through. When S1 and S0 are both 0, then we allow through X0. But for example, when S1 is 1 and S0 is 0, then 1, 0 is 2, and we want to allow through X2. The same goes for X1 and X3. However, this is just the equation from 4-input multiplexer, and we already have 12 terms. Something like this is not practical in the real world at all, especially if we have to switch between 8, 16, even 32 inputs. This equation would get way too big. Option 2 is to connect multiple multiplexers together. We can think of a 4-input multiplexer, where we have 4 inputs, 2 select lines, and 1 output, as two steps of 2-input multiplexers set up in the following configuration. The first mux is taken S0. If S0 is equal to 0, then that means that we're either selecting between I0 and I2. If S0 is equal to 1, that means that we're selecting between I1 and I3. Then this last multiplexer switches off the value of S1. So for example, let's say that S1 was 1 and S0 was 0. These two multiplexers would first select I0 and I2. Then we would get to this multiplexer, and selecting between I0 and I2, because S1 is 1, we would choose I2, and that would go to the output. With this information, you should be better equipped to start Lab 2. Come to office hours if you have any questions, or feel free to contact any of your PIs. Besides that, happy digital logicking.